Hello, Dr. Dorjin. My name is Marco Lucas Yahaan, and I'm a student number 1 now I would like to uh, present about principle of first and second law of the thermodynamics. And this is the table of contents that I would like to present right now. So, first, we have to know what is thermodynamics. Thermodynamics is the study of the effect of work, heat, and energy of the system. And thermodynamics deals only with the large scale of response of the system, which we can observe and measure in experiment. Now we enter the first law of the thermodynamics. First law of thermodynamics is energy can change one form to one form to another, but the total amount of energy remains constant. So, uh, in Hall system, the first law of thermodynamics tells us that energy is neither created nor destroyed. Thus, the energy of the universe is constant. However, energy can certainly be transferred from one part of the universe to another. And to work out of thermodynamics problem, we will need to isolate a certain portion of the universe or the systems from the remainder of the universe or the surroundings. And then the formula is delta E equals Q minus W. And this is the first law of thermodynamics. Delta E is the change of internal energy of the system. Q is heat transfer into or out of the system. And W is the work done by all the systems. And then there is internal energy. The internal energy encompasses many different things, including the kinetic energy that is associated with the motion of the atoms and the potential energy stored in the chemical bonds of the molecule. And uh, this is why we only worry about delta E, the change in the energy of the system. This is save us a lot of work. For example, if the temperature doesn't change, we can ignore the kinetic energy of the atoms. And the formula is delta E equals energy in minus the energy out. And we enter the process in the call system. First is isothermal process. Those processes in which the temperature remains fixed are termed isothermal process. This is often achieved by placing the system in thermostat or a constant temperature bed. And for an isothermal process, dT equals zero. Second is adiabatic process. Those processes in which no heat can flow to or out of the system are called adiabatic process. And adiabatic condition can be approached by carrying the process in an insulated container such as thermos bottle. And high vacuum and highly polished surface help to achieve thermal insulation. And the formula is P times V power of gamma equals constant. Third is isobaric process. Those processes which take place at constant pressure are called isobaric process. Uh, for instance, heating of water to its boiling point and its evaporation to take place at the same atmospheric pressure. And the formula is W equals P delta V. And the last one is isochoric process. Those processes in the volume remains constant are known as isophoric process. The heating of a substance in a non-expanding is a chamber. Non-expanding chamber is an example of isophoric process. And the formula is Q equals delta U. Now we enter open system steady flow. And in open system steady flow, pressure and specific volume are both property. It is convenient to group flow work and internal energy together to form a new intensive property, enthalpy H. That there's a formula H equals U plus P times V, where the unit is kilojoule over kilogram. Now we enter the control volume. For a single stream, the mass flow rate through the entire control volume remains constant, and the conservation of energy for a single stream steady flow system becomes like this. This is the initial of uh, formula, but we can simplify it until we get the final is Q minus W equals H2 minus H1. And the mass balance for a general steady flow system as given is mass flow rate out equals mass flow rate in. Now is nozzle and diffuser. A nozzle is device that increases the velocity of a fluid by reducing the pressure. A diffuser, on the other hand, increases pressure by reducing the velocity of the fluid. There are some general characteristics for nozzle and diffusers. Usually, the rate of heat transfer between the fluid that is flowing through the system with surrounding is small. That means it can be negligible. And the work involved when it comes to nozzle and diffuser are also negligible. Furthermore, change in potential and kinetic a change in potential is negligible. However, the fluid in nozzle and diffuser tends to experience large change in velocity, hence the kinetic energy will not be zero. And then we got the final formula is some mass flow rate in outside times h plus kinetic energy equals mass flow rate in uh, time multiplied by h plus kinetic energy. Turbine and compressor. Compressors are used to increase the pressure of a fluid. For the process, actually need to supply with power. In other words, work is input, and this usually supplied from external sources to the shaft. In simple term, compressor use power to increase the pressure of a fluid. But however, heat transfer and potential energy is usually negligible. Nevertheless, the fluid is velocity in the turbine tends to be high, and these fluids can experience large change in kinetic energy. Nonetheless, in certain cases, it is possible that kinetic energy change is relatively small compared to enthalpy change, in which case it can be negligible. And in compressor, potential energy and heat transfer is negligible unless there is internal cooling involved. And for compressor, the velocity change of the fluid is not significant, so kinetic energy is negligible. And the formula for turbine is work out plus mass flow rate H plus kinetic energy equals mass flow rate in plus H plus kinetic energy. And for compressor, it's only mass flow rate times H equals mass flow rate times H plus work in. Throttling valves is any device that restrict the flow of a fluid and reduce the pressure of the fluid. And in the heat transfer between the system and the surrounding in throttling valve are negligible, and the temperature remains constant and there are no work, so work is zero. Moreover, the potential energy and kinetic energy are also very small and can be negligible. And normally, interrupting valve have only one inlet and one outlet, means mass flow rate will be the same as mass flow rate are negligible. And for the formula for the valve, the final formula is H2 equals H1. In mixing chambers tend to be very well insulated, so heat transfer between the system and the surrounding are negligible. There are no work interaction as well, and the kinetic and potential energy of the fluid are also negligible. Each inlet and outlet have its own mass flow and enthalpy. Since this is steady flow, the outlet mass flow must be equal to the two inlet mass flow. And this is the formula for mixing chamber. Mass flow rate 1 plus mass flow rate 2 times H3 equals mass flow rate 1 times H1 plus mass flow rate 2 times 2 H2. For in heat exchanger, two fluid will exchange heat without mixing. If all heat exchanger to be selected in the system, then there's no heat transfer between the system and the surrounding. Furthermore, there is no work and potential and kinetic energy is negligible also. In heat exchanger, there are two separate input and two separate exits. The inlet has its own mass flow and enthalpy values, and the same goes for for the outlet. And the final formula for heat exchanger is mass flow rate B times H4 minus H3 equals mass flow rate A times H1 minus H2. So we enter the second law of thermodynamics. Second law of thermodynamics is state of entropy of the entire universe as an isolated system will always increase over time. And the second one also state that change in entropy in the universe can never be negative. And also in second law of thermodynamics, there are two theo- famous uh, theory, it is Kelvin-Planck and Clausius statement. Calvin-Planck's statement states it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce only a net amount of work. While it, for in Clausius' statement, it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. In other words, a refrigerator will not operate unless its compressor is driven by external power source. Now we enter heat engine. A heat engine is a device that operates in cycle in which heat is transferred from heat source to heat sink for continuous production of work. And for the formula is W net equals W out minus W in, while W in is amount of work required to compress water to boiler pressure and W out amount of work delivered by steam as it expands in turbine. And then thermal efficiency, the fraction of heat input that is converted to network output is measure of the performance of heat engine and is called the thermal efficiency. And for the formula is network output over total heat input. You can also express as eta eta thermal equals W net out over Q in, and also can be eta thermal plus 1 minus Q out over Q in, since we W net out equals Q in minus Q out. And then coefficient of performance or COP in refrigerators, and the formula is desired output over required input equals QL over W net in. And since W net in equals QH minus QL, then the COPR relation become COPR equals QL over QH minus QL equals 1 over QH over QL minus 1. And then in COP heat pumps, the formula uh, basically same with the refrigerator, but the make it difference is COPHP equals QH over QH minus QL equals 1 over 1 minus QL over QH. And so we can obtain COPHP with COPR plus 1. And then we enter the Carnot cycle. The efficiency of a heat engine cycle greatly depends on how the individual processes that make up the cycle are executed. The network or efficiency can be maximized by using reversible process. The best non-reversible cycle is the Carnot cycle. First, we have reversible isothermal expansion. The gas expands slowly, doing work on the surrounding. Reversible heat transfer from the heat source TH to the gas which is also at TH. And then for reversible adiabatic expansion, the cylinder piston is now insulated and gas continues to expand reversibly slowly. So the gas is doing work on the surrounding, and as a result of expansion of the gas, temperature reduced from TH to TL. The piston is assumed to be frictionless and the process to be quasi equilibrium, so the process is reversible as well as adiabatic. And then we have reversible isothermal compression. The gas is allowed to exchange heat with the sink at temperature TL as the gas is being slowly compressed. So the surrounding is doing work on the system and heat is transferred from the system to surrounding reversibly such that the gas temperature remains constant at TL. And then we have reversible adiabatic process. Reversible adiabatic compression. State 4 is such that when the low temperature reservoir is removed, the insulation is put back on the cylinder head. the gas is compressed in a reversible manner, so the gas returns to its initial state or state 1. And the gas temperature is increasing from TL to TH as a result of compression. And we got Carnot cycle PV diagram. And Carnot cycle is the most efficient cycle operating between two specified temperature limits. The efficiency of all reversible heat engines operating between the two same reservoirs at the same. And then we got the formula this eta thermal equals 1 minus QL over QH. And it can be shown with 1 minus TL over TH. Then we got the current refrigeration at heat pump cycle formula. For refrigerator, we got COPR equals 1 over QH over QL minus 1. And for COPHP, we got 1 over 1 minus QL over QH. Then for the isentropic process, a process during which the entropy remains constant is called isentropic process, and it can characterized by delta S equals 0. And for isentropic process of ideal gas can be obtained by setting entropy change relation equals to 0, and also when the constant specific heat assumption is valid. And we get the formula P1 V1 over T1 equals P2 V2 over T2, and V2 over V1 equals T2 P1 over T2 P2 equals T2 PR1 over T1 PR2 equals T2 over PR2 over T1 over PR1. And then the last one, we get the entropy change of ideal gases. For ideal gases, whole specific heats vary almost linearly in the temperature range of interest. The possible error is minimized by using specific heat values evaluated at the average temperature. And we got the formula S2 minus S1 equals CV average ln T2 over T1 plus R ln V2 over V1. And also we can change the CV to the CP average also, with the unit is kJ over kg times Kelvin. Next, we enter isentropic efficiency turbine. For a turbine under steady operation, the inlet state of the working fluid and the exhaust pressure are fixed. Therefore, the ideal process for a adiabatic turbine is an isentropic process between the inlet state and the exhaust pressure. And we get the formula is eta T equals actual turbine work over isentropic turbine work equals WA over WS. And usually the change in kinetic and potential energy associated with a fluid stream flowing through turbine are small relative to the change in enthalpy and can be neglected. And then the work output of an adiabatic turbine simply becomes the change in enthalpy. So we can get eta T equals H1 minus H2A over H1 minus H2S, where H2A and H2S are enthalpy value at the exit state for an actual and isentropic process respectively. And isentropic efficiency of compressor and pumps is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in isentropic manner to the actual work. So the formula is eta C equals isentropic compressor work over actual compressor work equals WS over WA. And also similar, the previous one become the adiabatic compressor becomes equal to the change in enthalpy. So basically the formula almost similar with the previous one, but the difference is the position H2S minus H1 over H2A minus H1. And when the change in potential and kinetic energy of a liquid are negligible, the isentropic efficiency of one is defined similarly as WS over WA equals V delta P over H2A minus H1. This is isentropic efficiency nozzles. And for the nozzle, the formula is eta N equals actual kinetic energy at nozzle exit over isentropic kinetic energy at nozzle exit. And then the isentropic efficiency of nozzle can be expressed in terms enthalpies are eta N equals H1 over H2A over H1 minus H2S. There S2A and so S also same, evaluate at nozzle exit for the actual and isentropic process respectively. And then a closed system involves normal flow across its boundaries, and its entropy change is simply the difference between the initial and the final entropy of the system. The entropy change of a closed system is due to entropy transfer accompanying heat transfer and the entropy degradation within the system boundaries. And then we got the formula is sum qk over qk plus s generation equals delta S system equals S2 minus S1, where the formula is kilojoule over Kelvin. And for an adiabatic process, the entropy transfer terms in the preceding relation drops out, and the entropy change of the closed system becomes equal to the entropy generation within the system boundary, where the formula is S generation equals delta S adiabatic system. So we reach the conclusion. The first law of thermodynamics relates the various forms of kinetic and potential energy in the system to the work which a system can perform and to the transfer of heat. This law is sometimes taken as the definition of internal energy and also introduce an additional state variable enthalpy. In addition, this study suggests that the purpose of the second law of thermodynamics is to describe the increase of entropy in irreversible process, imposing constraints on state transformation and emphasizing the directionality and irreversibility of natural process. And this is the reference to make me to assist me make this presentation. And I think that's all from me. Thank you very much for Dr. Nordin that already listening to me, and I asking apologies if I'm making a mistake during presentation. Thank you very much, Dr. Nordin.